Thank you.
Okay, I think we're going to go ahead and get started now. A couple of folks are still in line for food or a drink, but that's fine. If you guys could just be somewhat discreet as you find your seat, I think we'll get started. We have about an hour, just over an hour for Haresh, and he says he has about a 2-hour-long talk, right? So, no, he says he has about a half-hour to 45-minute long talk, and so hopefully the real ideal situation actually would be for him to give this talk and then have some real discourse, because he's very knowledgeable, and it would be great to hear some of your questions and some of the response. So we'll try to encourage that. So I'm up here to introduce him because of the folks here at CMU, I've probably known Haresh the longest. He is currently a program manager and has been for some time at EPRI, and he's focused mostly on energy storage, mostly on application of energy storage on mostly North American grid locations, correct? Yeah. So Haresh Hart, he's got both a bachelor's and a master's degree from Stanford University, both in chemical engineering, and has bounced around. He did a little bit of industrial work prior to his current situation at EPRI, but he's sort of a fixture now in the energy storage community. He is frequently called on to give talks around the country and indeed around the world on stationary storage that's grid-tied. And so it's a real honor to be able to have him here for us today. I'm thrilled to see the huge turnout, and I don't want to waste any more time. So without further ado, I'd like to welcome Haresh Kamath. Thank you.
Thank you, Jay. Thanks, everyone, for coming. As Jay said, I have a 2-hour presentation. Actually, it'll just seem like 2 hours. So hopefully not. Hopefully, I'll probably go about 30 minutes, and then, as Jay said, we'll have time for some questions, maybe some discussion. I'm interested in hearing ideas, and always interested in hearing ideas and thoughts in this area. It's very much an area of exploration right now. The thing you hear about energy storage, like many other technology areas, you hear a lot of rah-rah stuff about how great it is and how wonderful it is. And it is. I mean, there are a lot of things that are changing in this area, and it's becoming an opportunity, a real opportunity. There are also some challenges, and some of those things are the things that we need to address as a community to actualize the potential. And one of those challenges is even just understanding what are we doing here? What are we doing with energy storage, and why is this important? So these are some of the things I'll talk about today, and I'm just going to touch the surface on a lot of these things and encourage you to ask questions with that as we go forward. So to begin with, just talk about who I am and where I'm from. I'm coming from EPRI, the Electric Power Research Institute. We are a nonprofit research organization. We're funded largely by the electric utilities, but our mission is in the public interest. We are searching after those technologies that can ensure safe, reliable, affordable, and environmentally responsible electricity for everybody, for universal access. So although a lot of our work tends to be in developed countries and making sure that the cost of electricity is low, continues to be low, and the reliability is very high, a lot of what we're doing is also now being applied in developing nations, and we're hoping to expand our mission into really making sure that everybody, everywhere, has electric power to make their lives better. So, and we really believe in that mission. This is really about, electrification is a big deal. We've seen historically that people have produced power in various different ways. Electrification was one of the big steps up in human development. So when electricity became possible, when we started electric power, we really saw a step change in living conditions all across the world. And it ties together with many other things, of course. But that continues to be the case today. And as technology evolves, of course, so does the power system. This is something that all of you have probably seen. We're familiar with the power system of today. I should say maybe the power system of yesterday, because many of these things have already changed. Historically, we've had a very relatively simple power network with centralized generation here on the left side of this chart, And then the power is delivered through transmission and distribution out to customers who consume it. And so historically, it's been the job of the electric utility to generate and produce and provide power to the end user. Increasingly, as we go to tomorrow's power system, it's going to be much more complicated than that. Certainly, there's still going to be centralized generation, but that generation is going to have many more forms than even it does today. Some of it's going to be fossil, but some of it's also going to be renewable. Some of it's not as controllable as it used to be, but we have a much bigger diversity in sources than we did before. But even more importantly, we have assets down towards the edge of the grid that are generating and using power in different ways than they have historically done. We also have new technologies that will let us control the grid better than we have in the past. And so in the future, we can expect a highly interconnected power system to optimize energy resources. And the value of the utility, or the role of the utility, or the role of the grid operator, if you will, is going to be very different. Rather than generating electricity and delivering electricity, the real role of the grid is going to be to serve as a means of energy exchange between people who are using energy, but also maybe generating it from solar panels or from smaller systems, maybe natural gas-based electricity generation systems that are located close to the point of end use. So among the technologies that we are looking at is, of course, energy storage. And so some of these things are highlighted here on this chart. And we're looking at storage at different levels on the grid. We're looking at the bulk level, at the centralized area, where it can provide peaking and ramping services. We're looking at it at the distribution level, where it's more about power flow and controlling how power flows across the grid. And then we're also looking at it at the customer side of the meter, where it can be used to provide more reliability to the customer, but also be used to decouple loads from the grid. So you can use storage to manage how you use energy. That is extremely powerful for the end user. It can also be powerful for the grid. So by looking at the way energy storage can be used, we can understand how this might evolve in the future. Now, one thing to understand and to remember about energy storage, and we hear this story all the time. We hear this and we say, oh, well, energy storage is going to change everything. It's going to be the Holy Grail. And the Holy Grail thing I've always heard quite a bit, and I've always scratched my head a little bit because the Holy Grail doesn't exist, right? I mean, it's something it's not only a mythical goal, it's also a very perilous goal to achieve. Many people have tried, everybody has failed, and so on. And so, it's a strange metaphor to use. I don't think of energy storage as the Holy Grail. I think of energy storage as one more tool. We shouldn't think of it as the cure-all. We shouldn't think of this as the thing that gives you eternal life. We should think of it as one more tool in the toolkit for addressing where we want to go. And for that reason, when I get later on in applications, I'll talk about what that means. But that discussion about the Holy Grail really engenders some very interesting thoughts from people out there about where energy storage is. And many people are familiar with the Gartner hype curve about new technologies. New technologies tend to take off. When you first hear about the technology, nobody knows about it, but then it becomes something that's really overhyped. Everybody hears about it. And then it goes through a trough of disillusionment before reaching the plateau of productivity. And so for energy storage, we're already going through this process. Distribution energy storage is probably over the peak, already headed into the trough. Bulk energy storage is probably already in the trough. And what we've heard in the last couple of years, of course, is behind the meter storage, things like the Powerwall, Tesla Powerwall, which was announced almost a couple of years ago, about a year ago, I should say. And that's near the peak, maybe just past the peak. And then you hear about microgrids also, and that's somewhere close to the peak, I think. It's not to say these technologies don't have value. It's just that you got to be careful about the hype. What we really want to see is what the real value of these technologies is. And I would say that the value of technology right now is greater than where the market places it on the curve. So, but it's not as easy to realize as we might see. And really, what I want to talk about today is where this falls. What are the real facts, and what are the real potential possibilities of these technologies? So first, I want to say, okay, what has changed? So why are we talking about storage today, where we didn't talk about it, say, 30 years ago? And I think one of the big things that's really changed is in the technology. Historically, the technology has been very expensive. When you look back about 35 years and look at what people were talking about, most people were talking about lead-acid batteries. And it was very clear that lead-acid had potential in utility applications, but wasn't quite low-cost enough, wasn't quite long-lived enough for those types of applications. And now what we're seeing is a lot of newer technologies that have eclipsed lead acid. Certainly lithium ion is one of them, as we'll talk about, but there are other technologies as well that are very important in this area. Historically also, there have been a lot of economic challenges with storage. The values of storage are relatively low compared to the cost, and certainly the costs are coming down, but more importantly, we have new business models that can address that. And those business models include, in many cases, putting together a lot of different values to try to create a value proposition for storage. People are more patient with that type of approach these days than they were maybe 30 years ago, because we've seen that already happen with other technologies, things like computers and smartphones, which you don't really buy those things for an individual application. You buy those for a multitude of applications, right? And then you put that together to create a value proposition. And one of the value propositions that is coming out today in energy storage is, of course, what we're seeing in a lot of the energy industry is incentives. Government incentives for solar and for wind have made those technologies very viable from a monetary standpoint, so that they're investment-grade assets now. People invest in them because they have a steady stream of revenue that they're getting from those incentives. The same thing is happening in energy storage, where historically there was not a lot of definition on what storage was. There's now a sense from regulators and legislators that storage has value. And they're looking at that value in multiple ways. One is, of course, tied back to renewables. That there is a sense that renewables, because they're uncontrolled, you have to have storage. So the argument that's made, for example, solar energy is only available during the daytime. So if you want to use solar at night, well, then you're going to have to use storage. So a good argument, and so for that reason, people are promoting energy storage with solar. It doesn't make quite as much sense when you look at the grid as a whole, actually, because really what you're trying to do is serve those loads, and so you have to shift energy a little bit, but not as much as you might think. But it still makes sense from a theoretical perspective, and so certainly policymakers are looking at it and saying, well, this is maybe something we should encourage. And then equally important in the eyes of many policymakers, energy storage is seen as, again, the next big thing. If it is the next big thing, then we want to encourage it because it's economic development. We want to encourage companies to make this, we want to encourage that in our jurisdiction. So a lot of places are competing with each other to try to set themselves up as a center of excellence for energy storage. We'll see how well that works. With solar, it's a mixed bag. Germany certainly tried that in Germany with their policy approach and with solar, and it worked to a certain extent, but it may not have had quite the results that they expected. So we have to look at it a little carefully when we look at those things. But there are plenty of other things that are happening out there that are making regulators and legislators look at energy storage in a new light compared to what they saw this in several years ago. And you're seeing this across the board. It's not just about storage per se. It's about things like net metering, which historically has been the way that we deal with solar. You use the grid for storage. But if that's going to have negative impacts on the grid, maybe we should consider storage at the edge of the grid. Looking at renewable portfolio standards, if you want a renewable portfolio standard of greater than 50%, which is what many people are talking about, then you should consider cost-effective storage as part of your portfolio. as well as there's some other interesting things that are going on, like procurement targets. And in New York, we're seeing the New York Rev, which intuitively might have some incentives to offer for storage, and so on. In markets, we're seeing some things like the FlexiRamp approach. And here in Pennsylvania, certainly in the PJM area, you've seen a great deal of adoption of energy storage for frequency regulation. So interesting things are happening. And as with a lot of technologies in this area, policy tends to be a very heavy driver, for right or for wrong. I mean, I'm not saying it's doing the right thing. It tends to be a driver for a lot of this stuff. And in the near term anyway, policy tends to trump the economics, which tends to trump the technology. In the long run, it goes the other way. So in the end, we really have to make sure that from a technology standpoint, this makes sense, that it results in an economic value proposition before we can really say this is all going to happen for real. In the meantime, we still have many other challenges to address with energy storage. We still don't understand all of the cost and performance factors, and that makes people a little bit leery of investing in this area. That's perfectly legitimate. There's still a lot of research that needs to happen. But maybe even more basic than that, we don't know entirely how we're going to use energy storage. We've had a grid that operates very well without storage for 100 years, and the value proposition for storage is not as clear-cut as it is for, say, solar. Solar is delivering energy. You can pay for that energy, $1 per kilowatt hour. But what's storage delivering? It's not delivering energy. It's not, in the end, it's actually going to consume energy because there's an efficiency, right? So since you're not delivering energy, you're delivering some kind of service. You're delivering a service of being able to keep that energy away for you for a while. And does that have value? What value is that? Trying to understand that is very important to move forward. Making sure that storage technology is safe and reliable, and safe, secure, reliable, affordable, practical. All of those words are important. We have great technologies, but that doesn't necessarily mean we know how to use them on the grid. It's more than just taking a battery and then sticking it on the grid. You've got intervening technologies like the inverters, the balance of plant, and so on. We have to create best practices for deployment and operations and maintenance. Utilities are very unfamiliar with batteries in general, or in energy storage technologies in general. And certainly end users are unfamiliar with this for things like home assets. So the question is, can we do that? And then finally, just to integrate this into the whole process, the whole regulatory process, the whole economic process. And those things are things that just need to be done before we can really say, okay, this is a real market. So that's some of the work we're doing at EPRI. We're developing analysis tools to understand where the values of energy storage are. We're doing demonstrations with some of our members to show where the values of storage are and what are the challenges. Some of the things that we're finding, for example, is with respect to things like safety. With lithium-ion batteries, just as an example, we know that lithium-ion has got a propensity there are certain risks associated with lithium-ion batteries with respect to fire and other things. In fact, all batteries. In all energy storage systems, you're taking a whole bunch of energy and putting it in a small box. Well, energy wants to get out of that small box. And so if that's the case, then you have to address the safety issues related to that. And this is in particular true of lithium-ion because you're taking a lot of energy and managing to cram it into a relatively small box. And so the safety issues have been addressed at the small scale when you're talking about your cell phone or your laptop or even a vehicle. When you're talking about a huge 100-megawatt installation, then you have to take different approaches. And that's some of the things that we're investigating right now and have to be addressed before we really get to that scale. And again, that's true of any technology. A few years ago, we had a year in which we had a number of energy storage systems that encountered safety incidents, as we call them in the industry, or rapid venting, or whatever euphemism you want to use. They're fires, right? And it's just it was interesting because there were 3 different technologies involved. So you couldn't point it at any one technology and say, well, this technology is safe and that technology is not. All technologies have safety issues that need to be addressed, and that's one of the things that really needs to happen in the industry. And so a lot of that requires testing and demonstration to really make that happen. One of the things that we're doing at EPRI to try to address that is work with the industry, both vendors and developers, as well as utilities and consultants, government agencies, everybody across the board, to just try to bring people together to talk about these issues through the Energy Storage Integration Council. This is a free activity forum that we hold about twice a year, just to come together and talk about the issues that need to be addressed. And then we try to work with people like the national labs to make sure that they're being addressed. So, but really, again, going back to technologies, the question that we get about this stuff is, which technology do we use? And I think that's been the question that we've been trying to answer for 15 years plus. That's the question I keep getting even today. And the answer is, it depends on what you're trying to do, right? These technologies all have sweet spots, and they all fit in different places. This is kind of a little bit of an older slide. It doesn't have some of the newer technologies up there. I noticed that sodium ion, for example, is not on there. It doesn't have solid state batteries. It doesn't have, does that have metal air? Oh, it has a metal air up there. But there are lots of technologies out there, and all of them have a sweet spot. But one of the things right now that we're seeing is that, of course, a lot of things are being driven by cost. And so there are a few technologies that really have achieved that already, technologies that have been out there for decades, like lead-acid batteries, compressed air, and pumped hydro, which are out there quite a bit, have already been deployed. So when you look at technologies that have already been deployed, we know where the costs are, and those tend to be the most interesting in terms of deployment. So the question is, well, can any of the other technologies get to the point where they become ready to deploy? And of course, the one that has received a lot of attention recently is lithium ion, simply because there's so much investment going into it. People always ask, well, lithium ion is not really well suited for the grid, or not really well suited for other applications. But the issue is that it's very well suited for cell phones. It's very well suited for laptop computers. And that meant that a huge amount of investment went into lithium ion in the 90s and into the 2000s and into the present day, just to make a better cell phone, just to make a better laptop. That investment was ultimately applied to larger systems like electric vehicles and now like grid technologies. And that's really where this is all coming from. Billions of dollars invested into consumer electronics that is now rippling across the industry and going into other applications. So do these other technologies, does that mean the other technologies don't have a place? No, of course they have a place. But they need to see that investment. We need to see significantly more investment to see those guys take off. So in the near term anyway, we'll see lithium ion at least probably be the dominant technology in stationary in the next 5 to 10 years. After that, however, we'll probably see lithium ion begin to reach a saturation point. There's a lot of limits to what we can do. And so we'd like to see other new technologies develop that. We have seen the costs fall for lithium ion dramatically. In fact, we saw a tremendous drop in late 2015 in the prices of lithium ion. And according to our models, the prices are below the costs, which is very intriguing. Either our cost models are wrong or the vendors are selling below their costs. So that's a very interesting thing to see. I suspect it's because we've seen a tremendous amount of oversupply in the industry in the last few years. You hear a lot about the gigafactory. Tesla is building an enormous factory out in the desert to build lithium-ion batteries to bring the cost of batteries down. That's certainly a good way of doing it if you have the demand. The whole idea is to create a market in which the demand and the supply meet at a point where the price is very low, which is great. But if you just have the supply and you don't have the demand, then you've got a problem. It means you have a lot of excess capacity. And one of the things that is not touted in the industry is that the gigafactory is not the only large factory out there. In fact, there are 4 or 5 other facilities already of that size out there, well before Tesla's is even operational. It's just that Tesla can do this differently. It's a very interesting thing, really. Most companies, when you put several $billion into an asset, you try to keep that off of your balance sheet. You try to keep that away from the eyes of your investors, and you just say, well, we got a big factory that we've built somewhere. Whereas, Elon Musk can say it a very different way. He said, hey, look, we've built this huge factory, and this is big. So, because he's able to do that, because he's able to go in and say, hey, I've got this factory and this is happening, he's created a very different environment for batteries. A lot of the other guys out there are seeing that and are trying to match those prices, and I think that's what's really dropping these prices down, at least temporarily. We'll see what happens. We'll see what happens if the market doesn't materialize. In the near term, we probably will see a lot of pickup from the stationary industry, but again, a lot of that is going to depend on how it's used. So in the meantime, we're kind of relying on the electric vehicle market. And the electric vehicle market has been great, don't get me wrong. We have seen tremendous success in the uptake of electric vehicles. Certainly, we've been, at EPRI, we projected a significantly lower number, probably right around here. This is current as of the end of February, and we've seen over 400,000 EVs just in the US alone. And actually, the uptake has increased overseas, particularly in China. It's interesting. We've seen a tremendous uptick in electric vehicles being sold in China in the last year and a half or so. So this is a good story. However, the world out there is not expecting this. The world out there has made some incredible projections, and some of them are very unrealistic in terms of what they wanted to do. Because if you want to build this huge factory, then you've got to show your investors some unbelievable return. And so a lot of people said, oh, well, we're just going to see 2 million vehicles in 2 years. That doesn't happen. There's no real world in which that happens. And so unfortunately, even though I think the uptake of electric vehicles has been a lot faster than we expect, the story that goes out in the media is, wow, these are a disappointment. Nobody really who is in touch with this industry expected to sell 1 million EVs by 2015. That's just, that doesn't happen in this industry. This is an industry where people buy at a relatively small replacement rate, and you don't just simply go out and buy an EV, run out and buy an EV just because, well, they're there. So it's important to recognize that, and of course the battery companies in the meantime have to do something with their plants. So they're selling batteries very low cost to the grid. So all of that said, we've got this great technology, lithium ion, that's going to be really low cost and it's going to be used in a lot of different applications, right? Great. So what are we complaining about? They're really cheaper than anything we've got out there. But, well, yeah, but, we're still talking about a technology that makes a lot of sense at that cost point, at this cost point, $250 a kilowatt hour. It still makes a lot of sense, and actually it looks like it might compete with conventional generation, which is something. We never thought that would happen, but only at relatively short time frames. So if you look at it for sub-hourly time frames, if you talk about a 15-minute battery, then a 15-minute battery can compete on the grid right now. And we've seen tremendous amount of deployment in lithium-ion batteries, especially here in this area, in PJM, in that time frame, in the 15 to 30-minute time frame. We can probably make sense with this price up to about an hour or an hour and a half. We can make a good business case for energy storage. But if you actually tried to make a 4-hour battery, then it will probably be more expensive than a natural gas plant. So a lot of the sweet spot is down in the shorter durations. And while lithium-ion prices may come down even further, we think that they might, we think that there's a saturation point. And so that's the point at which you're really starting to look for new technologies, especially when you look at it from a scaling perspective. Right now, a lot of people are still using the old 18650 cell, which was developed in 1986. So we're talking about a 30-year-old technology. A lot of people talk about it and look at companies like Tesla, for example, who are using the 18650 in their electric vehicle pack. And they say, wow, this is really advanced technology. Not really. No, this is really old technology. And that was the brilliance. That was the brilliance of the Tesla approach, because they decided to go with a technology they understood very well, and which the world understood very well. And just to make it clear, this is exactly what happened in solar, right? For solar, we were looking at all of these brand new technologies, thin film, and there were guys out there who were doing thin film in all kinds of new ways. You heard about them, Solyndra and nanosolar and all of the technologies that happened about 10 years ago. But what was it that won? What won was good old-fashioned polysilicon, been developed, built since the 70s, and it's being deployed. And the reason is that we know how it operates. We know exactly how it operates. We're minimizing technical risk. So same thing here. We're minimizing technical risk by using a good old technology, not a new technology. That's great as far as it goes. Because then what do? I mean, we're talking, once we start looking for a 1 megawatt system, we're talking about putting, we're talking about putting 150,000 of these little cells in a trailer. And now we start to look at this and say, no, wait a minute, there's some risk involved in that. When you got 150,000 of these guys in a trailer, it's a risk. And if you're talking about, some people are out there talking about a 100 megawatt system, now they're not talking about a cell this small, but they're still talking about a relatively small cell. And if they used a cell like the 18650, that would be 30 million cells. So this is not a scale approach. This is not a good scale approach. And this is where you start to look at it and say, well, do we need to use a different approach to scale things? And this is where a lot of the newer technologies come from in this area. I put a few of them up here. Ambri is a company that's doing liquid metal. Equion you're probably familiar with. It's a product of CMU and Jay's company. Here, some people are doing stuff with lead acid, showing that you can teach an old technology new tricks. It's a 150-year-old technology, but it's a new area. And these guys are also based here in Pittsburgh, I think, or close by. A couple of companies here, Alveo, Alevo. They sound the same, but they're very different. Companies like Vision with their flow battery, EOS with their zinc hybrid cathode. A lot of people are out there looking at new technologies. And some of these technologies may hold the key to the next big thing. I often hear people asking about flow batteries in particular, and so I address that. Flow batteries are something that a lot of the grid folks like because it looks like it can scale, right? You can build a scale approach with this. With flow batteries, what you do is you have a stack which generates the electricity, and then you put all of your electrolytes in tanks. And so you just pump them through the stacks. And the nice thing about that is if you need more capacity, you just add more tanks. And that just adds more duration. Or if you want more power, you just add more stacks. And if you want more power and more capacity, you can add both. And so from a scaling perspective, it makes a lot of sense. Now, there are some fundamental chemistry issues with flow batteries. So I still think this is a little bit further off than some of the flow battery companies like to say. But it's a technology that deserves to be looked at. And then there's even more basic approaches like water heaters. Now this is a really interesting thing. Water heater is usually the set point is set at 125 degrees F here in the U.S. That factory set point is determined by what is safe, because you don't want the issue of scalding people, or causing any kind of harm. But you can raise that temperature set point up significantly, and suppose you could set it as high as 150. Well, between 150 and 125, you've got 3 kilowatt hours that you can store at home in your water tank. And the reason that's important is because you can use that water tank to basically moderate your energy draw, so that what you do is, rather than just using it steadily over the whole day to heat your water, you just heat your water at certain points and you superheat it to that 150 degrees. And you're saying, well, wait a minute, won't I get scalded? Well, what you do is you use a valve. You use a mixing valve back here at the top end of the water heater to mix it with cold water down to the right temperature. So as long as you have the right kind of system with that, and the control system that does that, then you can store energy with a water heater. And I'm going to tell you that a water heater is a lot cheaper than a lithium-ion battery. I mean, this is just water and steel, right? I mean, you can do a lot of things with that. And so people are already looking at this, and this has also got a lot of attention, and it's happening right here in Pennsylvania. So, and you can see how this can address directly the load shape that's being created by solar, the famous duck curve that you probably have heard about. So, And that gets me to, some other things. People always ask me, well, okay, water heaters, that's kind of interesting, but I want a real battery in my home. And especially last year, Tesla came out with the Powerwall, which is a residential battery. Now this is really interesting to me because the Powerwall is not the first. There were people who were doing residential batteries before. Tesla themselves have been doing residential batteries very quietly for 4 or 5 years. And they just haven't made a big deal about it because they wanted to be sure that they had a real good technology before releasing it. And so a lot of people said, well, this is premature. You released this thing. No, I mean, they've been working on this for a while. Don't think they haven't. At the same time, the Powerwall is, the timing for the Powerwall was, of course, impeccable because it was engineered. But that was something that intrigued a lot of people. Can I use this to go off grid? Can I use this with my solar to not need the grid at all? And a lot of folks out there played both sides of that. So Morgan Stanley came out with a paper a couple of years ago saying, well, we see the price of batteries along with the price of solar going so far down that you can go completely off grid in the next 5 to 10 years. And other people came up with their studies and they said, nah, this is not going to happen, in the near term. So what's the reality? And I'll talk about this. So one of the realities of this is that it's a lot harder to do residential storage than you might think. There are a lot of guys out there who've got systems. A lot of these systems were rushed out right after Tesla made their announcement, and some of them have been working on this for a while. But there's a range of these guys out here. One of these guys here, this is a Kickstarter project. You probably heard about it. Very interesting. They're going to do 2 kilowatts and they're going to run it through a 3-prong outlet. I don't think so, but that's okay. We'll see. Let's see if that happens. But be that as it may, I mean, the real issue here is, value. So you as a residential user, what are you getting out of this system? If you've got time of use rates, then you can shift from peak to off-peak at home with a battery. And there's literally hundreds of dollars of value in that. But the product costs a few thousand. So I don't think that that's going to make any money for anybody. So if you go out in front of people and say, well, I'll sell you this product for $4,000 and you'll make $200 over the next 10 years, I don't think too many people are going to buy that. It's not going to make sense. Customers can store solar power and use it during peak load if you've got a solar generation system. Here in the US, that doesn't make much sense because we have net metering. If you don't have net metering, it might make sense. But you need a pretty big battery, a lot bigger than what you've got here. You can do demand response programs. Again, we've got, there's some incentives for that, but this is an expensive way of doing demand response. The better way is to turn off your lights. It's much more effective. Same thing with demand peaks. And right now, most residential customers don't face demand peaks. They may in the near term. And if rates change to face demand peaks, then this makes more sense. Finally, customers get a higher level of reliability. And this is for real. You do get more reliability with the battery. But how much are you willing to pay for that reliability? Some people would really like that reliability, and so they're going to go out and pay several $1,000s for this in preference to a $400 gas generator. But we're not quite at that point. I don't think we're at that point here because our grid is really pretty reliable. And so the question becomes, what's this for? What's this for? And Solar City, who's a very close partner of Tesla, Elon Musk, who's Tesla's CEO, is the chairman of Solar City. So they said themselves, well, this is an offering. We're putting it out there. But it doesn't really make sense because from a net metering perspective, you don't need it. And so, we agree. That's not to say that residential storage can't be used. I mean, there's actually there's good value here. Certainly the reliability value is there, but a lot of the values are actually back to the grid. And we did some studies on this, and we looked at what we can do. And the PV energy shift is a certain amount of value for homeowners that have that, and demand charge reductions. But a lot of the revenue that can come to these kinds of systems is from ancillary services, meaning that you're actually offering services back to the grid. you're actually offering services back to both the distribution utility and to the market. So we think that's really where the value of residential systems come in. Eventually the cost will come down and maybe this will make more sense, but in the meantime, most of the value, at least in California, comes from policy incentives. That's okay too. I mean, if you have the policy incentives, why don't you use them? That's just kind of an observation, and we're not saying there's anything wrong with that. But for right now, I mean, it's the policy incentives that make this case. If you don't have the policy incentives, then the case is very weak for residential storage. So naturally, you're going to see a very different uptake of residential storage depending on where you are. In California, where these policy incentives exist, you might see some uptake. In the rest of the country where they don't exist, you won't see uptake. In Europe, where we don't have net metering, but they have a feed-in tariff, it might make more sense, because a feed-in tariff is very different from net metering. There you don't pay the same price going in and out. There, actually, the solar is less valuable these days than buying from the grid, so it makes a lot more sense to store the energy locally and use it. But it still doesn't make perfect economic sense. And now the question is, again, can we go off-grid? Well, you could, but again, look at the value. Most of your value is coming from offering it back to the grid. It's not from local. And your cost is still very high. If you actually were to try to go off-grid with batteries, and we see this in the foreseeable future, even if the cost of batteries drop, if you try to go off-grid, it's probably not a very good value proposition. And if you think about it, that makes sense. Networked stuff always is more valuable than non-networked stuff. That's just an observation of economics. You know, that's a matter of making a bigger market. The bigger the market, the more easy it is to moderate your resource. So you can take advantage of economies of scale. So we believe that it doesn't really make a lot of sense to go off grid. But of course, there are going to be some people who do it. So it'll be interesting to see how that evolves. You know, and in that, you know, a lot of the values going back to offering values back to the grid, you know, come from both distribution values, things like increasing asset utilization. This is an important one. It's something like called the parking lot effect. You've probably heard about this, but you know, have you ever seen parking lots, you know, in large retail stores? You know how they size a parking lot for a large retail store? They size a parking lot depending on the busiest day of the year, right? Which is the day after Christmas. So that's the only day in the year when the parking lot's full. The rest of the time, the parking lot is mostly empty. But you need it for that one day, so you build it. And the same thing is true of the grid. We build the grid for the busiest time of the year, those days when you have the most power, and most of the grid infrastructure is not used most of the rest of the time. So your asset utilization is pretty low. And PJM did a study a few years ago, and here in this region, it's about 40% on average, the average utilization. So on average, 60% of the grid is not used for more than 50% of the time. So using energy storage can help that by actually addressing peaks. So instead of building out the infrastructure, you just put an energy storage system out at the end of the line so that it provides the energy during those peak times rather than building the infrastructure all upstream. Those kinds of applications are important. And that includes storage at all levels. You can use residential storage for that too. And that's an area where we have a great deal of interest on that. Bulk applications are the same way. Bulk applications are more in the market in terms of if you're offering services back to the grid. But it also raises a very interesting case because you have to know what your priorities are. So if you're going to use it for distribution level stuff, for example, like the asset management, the asset utilization application that I talked about, then you want to make sure that that takes precedence over just simply selling into the market, doing buying and selling of services or buying and selling of energy. So you have to make a dispatch priority, and you have to make sure that you have the right kinds of communication platforms that sends the signals required to do all of this stuff. And this is stuff that we're working on right now. It's across the industry, utilities, the government agencies, and a lot of folks are involved in actually setting the standards for these types of approaches. So, and then finally, I want to just touch on how storage is being used for renewables. A lot of people talk about renewables like wind, and they say, well, we need storage to fill in these big blanks. So storage could capture these peaks and then fill in this big void. That's very, very difficult for storage to do today. It's very expensive. You would need huge batteries, which are going to be very expensive. If maybe future technologies will be low cost enough to capture that energy, but today it's very tough. So more of what we're using storage for now is just to control the ramps, so that it doesn't go up and down quite as severely. And that's actually a very valuable function, because otherwise you'd be ramping up your coal plants or your gas plants all the time, and that puts a lot of wear and tear on your coal and gas. So the energy storage is actually acting as a buffer. It's also letting those conventional fossil generators operate, and the fossil generators are the ones that are going to fill in the gap there. That's going to be much more cost effective, certainly in the near term. So what we will end up going to is, right now we have primarily a fossil grid with some renewables on there to clean it up. We may eventually go to a largely renewable grid with some fossil there to basically moderate the renewables. That makes a lot more sense. It's a lot cleaner. It's not maybe perfect. Maybe we want to go to a 100% renewable someday, but that, from an economic perspective, a grid with diversity it can capture a lot of that. And energy storage is a part of that, not by filling in the big voids, but by just moderating the small differences. And from that perspective, energy storage is really quite interesting, because it can operate in both directions, and that's really the value. Right now, the shock absorbing effort is going on using basically a generator that's operating at 50%, and so you move it up and down to try to capture that. But energy storage can actually absorb energy, and so it can actually operate both ways, which means that you get both up and down ramping capability, whereas a generator can only go positive, and demand response can only go negative. And so storage has that capability. So I'm going to finish up here. Basically, the big takeaway: storage is happening. We're seeing a lot of very favorable things. Falling costs, some good policies that are actually favoring storage in many ways, newer technologies that seem more capable than what we've seen historically, and I think an increased penetration of renewables, which is making the need more pronounced where it wasn't as pronounced many years ago. And so there's a lot of interest in storage. From a technology standpoint, we're seeing lithium ion be a dominant technology, but not the only technology. We're not seeing it drive everybody else out. And the reason, that's for very important reasons. It's because it can't do everything. And so there's a very keen appreciation of that among the end users. And the end users are very interested in looking at other technologies. They continue to be interested in that. That's much more the case in storage than it is, say, in solar, where pretty much everybody's given up on everything else. But we're still looking for new technologies in terms of integration. That's a big area, and I talked about that a little bit. In terms of communication, in terms of controls, in terms of just the physical asset, how do we hook it up and how do we use it? And then finally, from an application standpoint, we see the most value in distribution systems in the near term, maybe a few bulk system applications like frequency regulation. Residential systems may get some uptake, especially when you look at it with solar. It might make sense. We talk about net zero energy homes, what we prefer to call advanced energy communities. Those kinds of things are definitely something that are in the cards and may make a lot of sense in the future. But we don't see the grid going away. We think the grid connection offers a huge amount of value to end users, simply because they can connect to the grid, they connect to the marketplace of energy, and that gives a great deal of power to a consumer who is using both local energy resource and taking advantage of the diversity of the grid as not only an import source, but also an export source. So with that, I'm going to open the floor to any questions or comments, suggestions, complaints, anything else?
Can you guys hear me? Good. I've got a microphone here I can pass around to those who have questions. I think this is the first hand I saw, so I'll facilitate it as best as I can.
Good afternoon. My name is Shailendra Sinha, and I'm investment strategist for the equity markets, focusing on technology companies. I've got two questions for you. Can you shed some light on the emerging Lithium Triangle from the standpoint of geopolitics? And second, do you foresee any significant role for graphene in the energy storage industry?
Oh, two great questions. The Lithium Triangle. So lithium is undergoing a pretty interesting thing right now with the prices because of and I assume this is what you mean. Do you mean the lithium supply chain? Basically, yeah. So, which is, I think it's creating some interesting things. I think that in the long run, people have been convinced by the recent developments, which is the supply shock that's happening, which is not real, by the way. I mean, what's happened is that lithium prices have climbed incredibly in the last 6 months. And the reason that they've climbed is not because the actual lithium supply is limited, it's because people are trying to lock in long-term contracts, and the spot market has risen in speculation that, people are trying to do that. What it means is that people, a lot of the producers, the battery producers, are beginning to realize that they're beginning to influence the price of lithium. They weren't the major user of lithium before, but now they are. And because of that, they're looking at other supplies. They're probably going to redevelop supplies in North America, redevelop supplies in China, and that's probably going to result in a shrinking of the supply chain eventually. Certainly from the standpoint of actually moving stuff around, almost everybody is trying to shrink the supply chain to the point where you start with raw materials where you end up with the end product. So for example, Tesla is saying that they're going to reduce their cost. I mean, their whole cost reduction strategy is based on moving everything to North America. They're not going to produce batteries in China. They're not going to dig up lithium in South America. They're going to produce lithium in North America. They're going to make batteries in North America. They're going to sell cars in North America. And in fact, many of the other people are doing the same thing. So in China, BYD is saying the same thing. And so I think eventually that's going to go away, the transport. But I mean, naturally, it's going to really follow the economies of the supply chain. So if there's a way, if it eventually becomes that, Chile is still the lowest cost place for lithium, they're going to buy it there. So that's not going to change. For your other question about graphene, we see a lot of applications for graphene. It's a very interesting material. It's difficult to see in the near term, immediately that graphene is going to be the savior for battery technologies or anything like that. There's going to be some applications. I don't see anything that is a particular game changer in graphene the way that people talk about it. If there is, I mean, it's probably the 15 to 20 year time frame rather than before that.
Thank you. And just a quick addition to the China lithium or the Lithium Triangle question. What I've been seeing recently is that the prices in China have gone way up because of local demand, because of their EV ramp, and the clearing price of lithium carbonate, lithium hydroxide in China went way up because China producers had locked in a bunch of deals, and then everyone else jumped on those prices globally. Mm-hmm. So it's a really artificial situation, and it's not clear that it's very sustainable.
Right.
But people are certainly pocketing tremendous cash right now. And the other thing I'll say, I just did a study with one of my students, Rebecca, and to look at what's the actual dollar per kilowatt hour impact of these changes in lithium prices, and it's extraordinarily small.
Right.
So it's a weird thing how these markets can gain or lose a huge amount of money based on these fluctuations, but at a delivered pack level dollar per kilowatt hour impact, extremely small.
Yeah, that's an important point, and that's thank you for bringing that up, because lithium is not the major cost in lithium-ion batteries.
It's like tiny.
Right.
All right, other questions? Yes.
There's one back.
Om Nayak from Nayak Corporation. My question is about the energy storage as an industry, where it would go. You said it's mostly going to go on the distribution side, and now we see that the utilities are you're breaking the utilities up into already operating as distribution companies, generation companies, and transmission companies. Now, if the energy storage, is it going to be treated like a generation type device, and policy-wise, is utility as a company, whether it is transmission, distribution, or generation side, is going to come in a big way to take advantage of this, or are they going to be kind of locked out of it?
Yeah, great question. Thank you for asking that. I should, I guess, clarify that I think that energy storage will be used across, across the entire spectrum. It's like refrigeration. I compare it to refrigeration. Refrigeration changed the food supply chain by taking an extremely perishable product and extending the life. That's exactly what storage does with electricity. Right now, storage electricity is very, very perishable. You basically generate it at the same time you use it, and because it can't be stored in between. But now we're trying to create ways of storing it, so that's going to affect the supply chain. I think a lot of the value is going to appear in the distribution system, but absolutely it's going to be placed at generators, it's going to be placed at distribution systems, it's going to be placed at the residential side, and all of those guys are going to try to make money where they can. To specifically answer your question about how it's going to be treated, that is very much in flux with regulators. So historically, large-scale systems like pumped hydro have been treated as generation. And certainly, depending on the jurisdiction, storage can be treated either as a transmission distribution asset or as a generation asset. And because it's bidding into the market, in many cases, it's being treated as a generation asset. This comes into some very interesting things in some parts of the world. For example, in Texas, which runs its own market and has its own grid, Texas, the distribution companies, which are just wires companies there, wanted to buy energy storage to improve reliability. But the generators are extremely nervous about that because they will also let them hedge prices. So what is that asset? Is it a generator? I mean, it looks kind of like a generator if you're able to dispatch it on demand to deliver energy to reduce the spot price of energy, then it acts kind of like a generator in the market. So ERCOT, which is the market company there, is trying to figure that out and trying to determine how it's going to be treated. Here in PJM, I think, which is probably the most advanced market for storage, it's being treated as kind of a generation asset because it's being allowed to bid into the market and do all of those things. But certainly, it's being looked at by many distribution companies. So we'll see how regulators do with it. It's still very much up in the air.
Great, thanks. There's time for one more question, and as the moderator, I'm going to take that last question. And it's this. I feel like I think you're so correct with your assessment of the relative efficacy and economic viability of storage in sort of grid-tied or places where it could be available. But there are also a lot of places, especially internationally, where there are pockets where the story is very different. Either the main power source has been historically diesel, or there are other places where there's been a tremendous amount of residential solar installed to the extent that selling back to the grid is no longer viable for stability reasons. And now the only way to maintain value from the solar panels is to self-consume. So this would be a Germany or Hawaii or Australia, whereas the diesel situation is South Pacific, Indonesia, and these markets are growing really quickly. The value proposition for stored energy is much different. It's between, we're looking at 30 to 50 cents per kilowatt hour delivered, and all of a sudden storage plus PV makes a lot of sense. It's a relatively smaller market than a developed country grid, but it's still quite large. And I'm just wondering if you guys have done much analysis as this is a contrast to these analyses that you show, and so the thesis that we have is that's the place to start, and then you eventually cost down and come to these places where it's way more economically constrained. I'm just curious what you think of that.
Absolutely. No, we have done quite a bit of study in those areas, and we agree. I mean, that's so. So first, I mean, so to look at the points independently, we've done quite a bit of work in the places like Germany and Hawaii kind of situation where we think storage can, basically in those cases, storage aids the further penetration of solar. solar resource. And that's really where we come to talk about advanced energy communities. I mean, that's possible anywhere. That's possible here too. And where you're talking about solar plus storage, creating a relatively easy way of improving generation without upgrading the grid substantially. And that is kind of the same application that we talked about with, having a grid but putting less strain on it. So that's, I think it's a great way of going forward. I think it's very important that we do that. From a manufacturer standpoint, as you're a storage vendor, you should absolutely be looking at that market, because that's probably the most important market there is right now. In the long run, it's different. But the one concern that we have about that is right now the path that that's taking is very uncoordinated. So the value that those things would have is if you could really do it as a coordinated approach that lets people be prosumers, if you will. The word in Europe is prosumer, which is kind of this portmanteau of producer plus consumer, right? So you're creating a energy grid that again is not designed to deliver the maximum amount of energy, but it's just designed to trade relatively small amounts of energy between homes. And in places like that, storage makes a lot of sense, brings a lot of value to the grid, as long as it's coordinated, as long as it's planned for. And that's really what we'd like to see. The other application that you mentioned, off-grid applications, I mean, energy storage there is absolutely an enabling technology. We've looked at that for a long time. I personally have looked at that. And historically, when you did this, it would make sense to put solar in those kinds of applications 20 years ago. You could do that in the 90s and make sense with deployment in developing countries where they don't have a grid already. It's cheaper than diesel. The problem was that the need was at night. And so you needed to shift that energy. And if you brought in a battery at that time, any cost-effective battery that was there, the lead-acid battery, for instance, would not last long enough to pay for itself. So today, with low-cost batteries, if you can hit the cost target of lead-acid and have a 10 or 20-year life, you've made it. I mean, that's an enabling technology. Now, the market is smaller because there's less money there, but it's still a very good market.
Great. All right. Well, with that, the last thing is Debbie's going to show up, I think, a plug for the folks who are here. Well, exactly. But I was going to applause after this. But anyway, thank you.
Yeah. Hi, everybody. I'm Debbie Stein. For those of you who don't know me, I'm Associate Director for the Institute for Energy Innovation and a Professor of the Practice in Engineering Public Policy. So I believe my computer is coming out here. While I'm doing that, I'm sort of the mind behind the madness that is Energy Week. So the fact that I'm standing here is a good sign. I'd like to invite our sponsors who are out there. If they want to come to the stage, I'll give you a few minutes to say something about your technology and your things. So here we go. So if anybody wants to come up, then you can just say like a few words about what it is you're doing. You'll see that some of these people back here have jobs. So given that we generally have a large engineering population looking for jobs, I hope that you will consider visiting all these different locations.
Go ahead.
And
1 minute.
Here we go. So I'd like to thank our sponsors. That's Duquesne Light, Mitsubishi Electric, NAYAC Corporation, Hite Corporation, the Sustainable Energy Fund. We also have other tables back there. The Entertainment Technology Center has an educational activity called Jewel that's very interesting. The Shale Gas Innovation Commercialization Center, Cyclotron Road, the Center for Sustainable Shale Development. I want to invite everybody back in a few hours. We're going to have the founders of Barefoot College. This is an organization that trains women to install solar collectors, to install and maintain solar collectors in India and Africa. So for those of you interested in developing countries, I hope you will come back for that presentation. That is at 4:45. And then there's also a student workshop, which is right after that, where you can get some more in-depth training for those of you who are, from emerging economies or would like to work in those areas. You'll see here that there's this general registration form, the CMU registration form. You can use that for our field trips, which are tomorrow morning. That's sort of the big last thing for our Energy Week activities. They're going to Duquesne Light, the Eaton Power System Experience Center, the Energy Innovation Center, Thar Energy, which is geothermal, Cube Hydro, which is hydropower, Mitsubishi Electric, the National Energy Technology Lab, People's Natural Gas, and the Phipps Conservatory. So there's still a little bit of a space in some of these tours. Also, I'm sorry, I forgot EQT, which is shale gas, the solar power, scale of solar, and wind power. If you want to sign up for any of these or find out more detailed information, go to cmuenergyweek.org. Great. Thank you very much. Please visit our sponsors who have all sorts of little interesting things, including chocolate and flashlights and all sorts of stuff. Thank you very much.